Okay, so let's start. Hello, everyone. So it is my great pleasure to introduce Professor Masahito Ueda from University of Tokyo. So I believe that you already know Professor Ueda with his great academic accomplishment, but let me briefly introduce him. So he is now currently professor in Department of Physics of University of Tokyo, and he is also director of Institute for Physics of Intelligence Center, which he just introduced me very briefly, but it was quite interesting. Also, he's a team leader of RIKEN, Center for Emergent Matter Science. His research area is Bose-Einstein condensate, fermions fluid, topological phenomena, and recently he did many interesting work in non-hermitian systems and influenced a lot of young scientists, including me. So today he's going to talk about this beyond-hermitian quantum physics. So Professor Ueda, you may start your talk. Yeah.
So thank you very much for the overly generous introduction. So first of all, I'd like to thank the organizers of APCTP for their kind invitation. So today I'd like to talk about an emerging new research field of beyond-hermitian quantum physics. So this is the outline of my talk. I will first explain why beyond-hermitian quantum physics is interesting. I will then review some basics of non-hermitian physics, and then discuss illustrative examples, including quantum transport, critical phenomena, and quantum magnetism. I will then discuss topological classification of non-hermitian physics before concluding this talk. Let's begin by discussing why beyond-hermitian physics is interesting. We first note that hermiticity is the most fundamental premise in quantum mechanics. It ensures a unitary time evolution of closed quantum systems, guarantees real valuedness of the eigenspectrum, orthogonality of eigenstates, and a transpose of an observable is equal to its complex conjugate. Once we go beyond hermiticity, then this implies the removal of these fundamental constraints and hence liberate us to new research arenas, new possibilities.
Sorry, an elementary question. So in
Yes.
the first example, unitary time evolution, does it, related with, so suppose I have some negative norm state, that's nothing to do with hermiticity, no?
Yeah, Hamiltonian is Hermitian. Therefore, the time evolution is unitary for this case. But if the system is open to environment, and if you look only at the evolution of the system alone, then time evolution is not unitary, but governed by Lindbladian.
I see. Yeah, thank you.
Yeah. So unitary evolution is applicable only for isolated quantum systems. Once the system is open or subject to measurement, then the system evolution becomes non-unitary. Okay, so there are two prototypical situations where Hermitian physics does a job. One is isolated quantum systems, which are described by Hermitian Hamiltonians. The other is systems interacting with well-characterized environment, so that the entire system is described by system path Hermitian Hamiltonian. However, in open systems, the survival probability decays and energy level broadens. In such situations, an effective non-Hermitian description often has proven effective. A classic example include radioactive decay of a nucleus, first started by Gamow, and the Weishaupt-Wigner theory of spontaneous emission. A rich variety of classical and quantum systems have successfully been described by non-Hermitian physics, which include photonics, mechanics, electrical circuit, stochastic processes, soft matter and fluid, nuclear reactions, mesoscopic physics, open quantum systems, and quantum measurement. And non-Hermitian physics thus applies to both classical and quantum systems. So in this talk, we focus on the last two subjects, namely open quantum systems and systems involving quantum measurement. There are two experimental milestones on these subjects. So the first milestone is continuous measurement of photon number. The group of Serge Haroche measured the cavity photon field by injecting atoms one by one into the cavity. As time goes on, the cavity photon field undergoes continuous state reduction to the number state of 5 for this left panel and the number state of 7 photons for the right panel. The similar continuous measurement can be performed on bosonic and fermionic atoms in an optical lattice. By using Bayesian inference, one can measure the atomic position beyond the diffraction limit. The second milestone is the development of quantum gas microscope. By placing a microscope just above an optical lattice, one can resolve atoms one by one as shown in these panels. So this technique has revolutionized our view about many-body physics, which can now be probed at a single atom resolution.
So elementary question, I think, yeah, I didn't understand it. Yeah. I mean, in the previous page, yeah. So you mentioned, yeah, this. So simply, I think I didn't understand. Will you elaborate more on this experiment and the meaning of, yeah, why it breaks through? Sorry.
Okay, so let me explain the experiment on this left panel by Professor Serge Haroche. So they have a superconducting cavity which perfectly encloses photon field in a superconducting cavity. And in this cavity, they put atoms one by one. Atoms are initially in the ground state. And then they measure the state of the output atom. If the output atom is excited, this means that this atom has absorbed a single photon. So this signals the detection of a single photon. But if the output atom is still in the ground state, then this means that no photon was detected. Now, by this experimental technique, they measured the photon distribution as a function of time. Yes. And the left panel shows initial distribution is Poissonian because initial photon field is a coherent state. But as time goes on, then the state collapses to a number state. In this case, the number is 5. And in the right panel, then the state collapses to a photon number state itself.
Okay. Thank you.
Okay, and this is truly remarkable real-time observation of wave function collapse, and this is why Serge Haroche obtained Nobel Prize. Okay, so in this case, they did similar experiment for atoms. Here, the atoms are placed in an optical lattice and big microscope is placed above that. And through this microscope, they are able to observe single atoms here, one by one. So it is, again, truly remarkable. And then when I look at this, then I have the following question. So this is really great. And at such high resolution, how about Heisenberg's uncertainty relation? This should no longer be ignored because we can now resolve atoms one by one, and the spatial resolution is good. Then the higher the resolution, the greater the measurement back action on momentum sector will be. And we thus expect many body dynamics and the quantum phase transition should be ordered by measurement back action. So remember that we have statistical mechanics because we thought we cannot trace atomic atomic group at a level of single atom resolution. But now they are able to do this, but at the expense of measurement back action. How measurement back action alters the statistical mechanical property is, I think, is an interesting current issue. So let us now review some basics of Beyond-hermitian physics. The Beyond-hermitian physics typically appears under continuous measurement. The two prototypical examples are photon counting and position measurement. A continuous quantum measurement consists of two processes, a jump process and a no jump process. So this is a time, and in each infinitesimal time resolution delta t, only one of them occurs. For example, in this figure, two quantum jumps occurs here and there, and no quantum jump occurring during the rest of the time interval. So in general, there are different types of quantum jump processes corresponding to different types of quantum jumps. Because quantum jump occurs between different levels. So depending on that, type of quantum jumps also differ. So suppose that there are m types of quantum jumps described by quantum jump operator L sub m. The unnormalized density operator immediately after the quantum jump is given by this expression. So here, rho is a pre-measurement density operator, and the delta t is a resolution time, and gamma is the strength of the measurement. The state change during a no jump process is described by this non-hermitian Hamiltonian H effective, which is constructed in terms of the jump operator as this. Here, H is the Hermitian part, and gamma is the non-Hermitian part. And this effective Hamiltonian, this one, actually can be derived from the requirement that the sum of probability of jump process and no jump process is equal to 1. Okay. So the form of non-Hermitian Hamiltonian is actually uniquely determined. And each individual realization of a quantum trajectory is specific by a sequence of measurement times, where T1 to Tn is a time of quantum jumps, and M1 to Mn describes the type of quantum jumps. So if a jump operator does not commute with the Hamiltonian, then the measurement can heat or cool the systems as described in these references. And this fact has also an important implication on quantum thermalization, as described in this paper. So non-Hermitian physics can be best illustrated by considering a continuous photon number measurement. So let us consider measuring the photon number in the cavity. So this one. And as I described in the experiment of Professor Saj Harush, actually he did exactly this. So they inject ground state two-level atom one by one into the optical cavity and measured the state of output atom. If the output atom is found to be in the excited state like this, then we judge that one photon is detected. And in this case, the post-measurement density operator rho prime is related to the pre-measurement density operator rho through this relation. Because one photon is detected, so one photon must be annihilated like this. So A is annihilation. Then if the output atom remains in the ground state, this means that no photon was detected, no jump process. And the density operator is given by this. So thus the no photon process is described by this non-hermitian Hamiltonian, which is actually not Hermitian, but anti-Hermitian because of the pure imaginary I. Thus, the non-Hermitian description can be justified in the no jump process, namely when no quantum jumps occurs. There are two important cases.
Professor Ueda, can you elaborate me more what the lambda would be, the physical meaning of the lambda in this setup?
So lambda is a coupling between this two-level atom and the photon field.
I see.
Yeah. So because of the lambda, so the state of the two-level atom can change. Yes. So this is the coupling constant. Thank you very much.
Related question. So
yes.
Suppose I start from the full system, which is complete Hermitian. So will you elaborate more on this reduction procedure to obtain this effective non-hermitian Hamiltonian?
Okay. So what we actually do is the following. So we have Hamiltonian for two-level atoms. We have a Hamiltonian for the photon field, which is just h bar omega A daga A. This is a two-level atom Hamiltonian is a Pauli, can be described in terms of Pauli matrices. And we have the coupling between them, which is usual Jaynes-Cummings Hamiltonian. Okay, so this is a Hamiltonian. And we let the system evolve unitarily. During the time that this time is specified by the time needed for each atom to pass through the cavity, the interaction time. After this unitary time evolution, then we perform projective measurement on the atom here. So this is non-unitary because we have a projection measurement on the atomic state. Then, depending on the outcome, whether it remains in the ground state or it is excited state, we have this case or this case.
Hello, can I ask just one question?
Yes, please.
My name is Jaegon Park from Seoul National University. I'm experimentalist working on magnetism. So I have very simple question. I remember in early 90s, Anupam and the Leggett studied a very similar system, two-level and the dissipation with the thermal bath, and studied the quantum coherence.
Yes.
And I'm just wondering whether there is any connection between their work and the work which we're going to mention today.
Yes. Thank you very much for this important question. The relation is this. So here we distinguish the case of output atoms, state of output atom. I mean, excited states, then this one, this case, ground state, then the latter one. Okay. When Professor Leggett discussed is a case that they do not distinguish the output state of output atoms. So in that case, we statistically take the average of this jump process case with probability of this, and no jump process with probability of this. So if we take an ensemble average of both cases, then we end up with a quantum master equation, which is consistent with what Professor Leggett did.
So just one more question. So are you saying that the non-hermitian physics should be should exist in their the model too?
Actually, in their model, since they already average out the outcome, so their description is consistent with the quantum master equation, Ginibre equation, or something like that. And non-hermitian physics is actually present but hidden because they already average both cases, no jump and out, no jump and jump process. Non-hermitian physics, non-hermitian physics manifests itself only if we focus on no jump process. Yeah, so it's hidden.
I see. So what you're saying is that in order to see that non-hermitian physics in real world, it's very important to distinguish actually finite states individually.
Yes.
Right. Okay. Thank you.
Thank you for this question. Okay. However, there are two important cases in which quantum jumps can be ignored. And hence, non-hermitian description is universally justified. So one case is coherent optics, because coherent state alpha is an eigenstate of annihilation operator, hence invariant against quantum jumps. So coherent state is an eigenstate of annihilation operator. Therefore, even if quantum jump occurs, the state does not change. The only state change during no count process is important. So this is why non-hermitian physics first experimentally flourished in the field of optics. Okay. The second example is Bose-Einstein condensate. In this case, annihilation operator indeed changes the number of atoms by 1. But since the number of condensed atoms is huge, so this change is negligible. So therefore, the Bose-Einstein condensate can also be well described by non-hermitian physics. Okay, so let us next discuss continuous measurement, position measurement of atoms in optical cavity. So we shine off-resonant laser light on atoms and measure the scattered photon on a screen by some detector. In this case, the measurement operator M is described by the strength of measurement gamma and the point spread function of the optical system F and the atom number operator Nm. M is a site of each atom. The dynamics of atoms under continuous monitoring is governed by 3 terms. The unitary evolution, according to the Hermitian Hamiltonian of the system. The non-unitary evolution in the absence of photodetection corresponding to no jump process. And the term describes the jump process upon photodetection. Thus, for both discrete and continuous observables, dynamics of the system under continuous quantum measurement consists of 3 distinct parts. First, unitary dynamics described by Hermitian Hamiltonian. Second, no jump process described by non-Hermitian Hamiltonian. And lastly, quantum jump process described by quantum jump operator. So let us now discuss a few illustrative examples of Beyond-hermitian dynamics. The first example is a two-particle quantum works under continuous observation. So we initially place two particles at adjacent position of the optical lattice. Then we let the system evolve freely, subject to continuous monitoring, and see what happens. So we compare such quantum transport for distinguishable particles, fermions, and bosons. So let us first consider the case of distinguishable particles. Continuous measurement of distinguishable particle can be modeled by a generalization of the single particle model due to DOC. So DOC already described the theory for a single particle some 30 years ago. And this is simple generalization of this model to a many particle case. The state evolution involves the unitary part, the first part, and the part that leads to the center of mass decoherence, and the part that leads to the relative positional decoherence. So all degrees of freedom can be distinguished for distinguishable particle, subject to measurement back action. In contrast, for indistinguishable particles, the relative position cannot be distinguished. In fact, the relative positional part is cancelled out due to two-particle interference. So the difference is this. So suppose that there are two particles to the detector. Okay. But there are cases when two particles cross in the between, in the midway to the particle. So this and this can be distinguished for distinguishable particle, but cannot be distinguished for indistinguishable particles. Therefore, there is a many particle interference, and it turns out that leads to the complete cancellation of relative positional decoherence. So this is the result of numerical simulation. So without measurement, then two particles move away in opposite direction, this and this. And the density profile is almost independent of quantum statistics. So distinguishable fermions, the bosons, they look almost the same. However, under continuous observation, we find very different behavior for distinguishable particles, fermions, and bosons. This random behavior is due to the back action of photon scattering. So we probe the atoms by injecting photons, shining photons, and there are random back action. But interestingly, they look quiet and they behave very differently for fermions and bosons. For distinguishable particles, measurement back action causes both center of mass and relative positional decoherence. Hence, the system shows uncorrelated, diffusive random walk. For distinguishable particles, however, only center of mass decoheres. Consequently, the center of mass coordinate is localized. So in this case, center of mass is at the center. In this case, center of mass is here. And the particles show strongly correlated ballistic transport. Moreover, fermions show anti-bunching because of the Pauli exclusion principle. And the bosons show bunching because of bosonic stimulation. So in the case of bosons, interestingly, they move in the same direction. So we next discuss the critical phenomena under continuous observation. The model we consider is a continuously monitored quantum many-body system. In general, a single quantum trajectory involves quantum jumps, but we first focus on the dynamics between two quantum jumps. Then the dynamics is governed by the effective Hamiltonian, like this. And this non-hermitian term describes the measurement back action in the absence of quantum jumps. So here, in the following discussion, for the time being, we ignore these quantum jumps. A non-hermitian Hamiltonian, this one, in general has complex eigenvalues. The real part is an effective energy of the system, and the imaginary part describes the decay rate. The effective ground state is identified as the eigenstate of H effective having the lowest eigenvalue, E lambda. And in our model, this ground state also has a minimal decay rate and hence the longest lifetime.
Question?
Yes, please.
I think I still didn't understand the elementary point. So how can you construct the non-hermitian part of the Hamiltonian? Maybe I repeat the previous question again.
Say again, please.
How can you construct the non-hermitian part of the Hamiltonian?
This part?
Yeah. What is
Okay,
the physics? Sorry, yeah.
Yeah, this is important. So thanks for the question. This is due to the conservation of probability. I mean, so let's see. The principle is this. So we perform continuous measurement and we assign some fine non-zero but very tiny time resolution. And we assume that in each time only two events occurs. That is, quantum jump occurs or no quantum jump occurs. So they are exclusive events. Therefore, the probability of jump process and the probability of no jump process must be equal to 1. Okay, so this is the first requirement, and then we can, for each quantum jump, we can specify what quantum jump occurs, and which from this information we know the jump operator. For example, photon counting, this LM is an annihilation operator of a photon. Okay, so this part we know.
I see.
And this part we have yet to know. But in order to strictly satisfy this condition, then this effective Hamiltonian must take the form of this. Because, you know, look at this trace, we take the trace to obtain the probability. Then if we take the trace, then this LM can go to the right-hand side. Therefore, gamma is given by L dagger L.
Thank you very much. Yeah, thank you.
Yeah, thank you very much for this important question. Okay. So now we consider the quantum walk. Next, we consider the situation in which Hermitian part of the Hamiltonian exhibit quantum criticality. So we are now about to discuss quantum critical phenomena under continuous observation. So one example is a superfluid motto-insulator transition in the Bose-Hubbard model. In this case, jump process is a two-body loss due to inelastic collisions. So therefore, the jump operator is BI squared. I is a position of an atom, and B is an annihilation operator of a boson. And the superfluid motto-insulator transition point is identified with a point at which the energy gap closes. So this is the result of the calculation. And this right panel shows that the phase transition point shifts as a function of measurement strength. So, so this is the amount of shift, how the phase transition point shift. And it shows that as the measurement strength increases, the phase shift becomes larger. So this means that this is a multi-insulator superfluid phase diagram. And this result shows that as the measurement strength increases, then this insulating phase, which is called mod lobe, expands. Why measurement expand multi-insulating phase? The reason is that quantum Zeno effect. The expansion of mod lobe may be interpreted as being caused by the suppression of hopping due to continuous quantum measurement. So if you observe atoms, atoms cannot move due to the Zeno effect. This implies that effective mass of atom becomes larger because it's more difficult to move under continuous observation, so the effective mass increases. Therefore, the insulating part expands. So now let's next discuss.
Question?
Yes, please.
How can you solve this problem, actually? How can you solve? Yeah.
That's a numerical calculation, simulation.
Suppose I'm trying to this in the some analytical path integral was and so Gelman-Law theorem will not hold. I mean, elementary question. So how can I consider setup for this superfluid mode insulate with this measurement?
Sorry, could you repeat the question?
Suppose how can I? So if I try to understand this critical phenomena based on some algae or whatever, so in the path integral way, can I construct how? So Gelman-Law theorem will not hold. I mean, so I have no feeling about So maybe some too much primitive question.
Yeah, I think this is an interesting question. I mean, how to formulate this in terms of path integral? Yeah, I think this is interesting. I mean, in this case, we solve this actually by directly solving, numerically solving non-hermitian Hamiltonian. And we also did strong coupling expansion. So this is an exact diagonalization result, and this is a perturbation of mean field. And we also did strong coupling expansion. They all seem consistent. However, so I mean, you are actually mentioning how to perform path integration.
In the algae, because critical to understand whatever.
That I think is an interesting question. And for example, convergence is okay for the non-Hermitian case, but how to actually carry out path integration is I think is an interesting question.
And may I ask a related question?
Please.
So I suppose one thing you can do classically is to construct Lagrangian, which would give you the same equation of motion as the one you're obtaining from this non-Hermitian Hamiltonian. I mean, in this case, I mean, is this classical? I mean, is it okay to? Can you show or disprove that either prove or disprove that this this kind of classical Lagrangian can be used for path integration, path integral formation?
I think this is an open question. No one has actually carried out this problem. I mean, path integration for this non-Hermitian Lagrangian. Intuitively speaking, I think convergence is okay because non-Hermitian, no count, no jump process usually decay the probability amplitude exponentially. So, but from a mathematical point of view, I have no idea, about what the outcome is. So maybe I suggest that it's good to perform analytically solvable path integration. For example, just take a harmonic oscillator and take the coupling constant to introduce a coupling constant with some imaginary, having some imaginary part, and carry out a calculation and see what happens. Yes.
Can I ask one question?
Yes, please.
I have a question about your interpretations. So by continuous quantum measurement, you seem to be introduce randomness, and the idea you thought to be is to describe it, at least to me, sound almost similar to Anderson localizations. And you're absolutely right that Anderson localization can increase in its mass. We know that localization physics, but that physics is different from the mode physics. So I wonder whether you can distinguish between the moteness and also this randomness induced in its localization physics.
Yeah, this is quite stimulating question. So my answer is this. So Anderson localization is essentially one body issue. So it is caused by the interference of single particle wave function due to random impurities. Okay, so this is the physics of Anderson localization. Mode insulation is caused by interparticle interaction. And in our case, it is indeed caused by interaction, B-daga, B-daga, BB. Actually, this is a loss, not interaction. If it is an interaction, then coefficient must be real. Yeah, but since this is a two-body loss, so we have an imaginary part. Yes. So, interestingly, this imaginary part leads to the localization, via the loss. And since this is not one body process, so it is very similar phenomenologically, but different from Anderson localization.
Right. Okay. Thank you.
Yeah. Thank you very much for this stimulating question. Okay. So let's next discuss the quantum criticality of 1D Bose gas. So the jump process is again the two-body loss. So in this case, the Hamiltonian is modified by the Lieb-Liniger model, which includes an imaginary coupling due to two-body loss. So this has been experimentally realized. So in the cold atoms, they confine atoms in the 1D potential, but atoms undergo two-body loss. So the effective Hamiltonian is something like this. So in addition to this real part, which describes the real interaction, particle-particle interaction, but we have an imaginary part. And the corresponding low energy model is a non-Hermitian Tomonaga-Rattinger liquid model, where the two-body loss is described by the complex phase that's described by this. We examine how critical exponents are modified by measurement. One critical exponent concerns one particle correlation function, which decays algebraically with a critical exponent k phi. The other is a density correlation function, which again decays algebraically with another critical exponent. So these two critical exponents, k phi and k theta, are equal for the Tomonaga-Rattinger liquid universality class. So here we plot them against the measurement strengths for weakly interacting case and strongly interacting case. We clearly see that those two critical exponents deviate significantly as we increase the strength of measurement. So they become different, which implies, so two different critical exponents indicate the emergence of a unique 1D critical phenomena, 1D quantum critical universality class caused by measurement back action. So measurement back action indeed creates a new universality class. So as a final example, let me discuss quantum magnetism in dissipative Hubbard model. So we consider the Fermi-Hubbard model in the multi-insulating phase. At half filling, an antiferromagnetic long-range order was already observed in this experiment in lithium-6 atom using quantum gas microscope. We use the quantum master equation to describe
elementary question. What does it mean antiferromagnetism in lithium? What does it mean antiferromagnetism in this?
Yes. Yeah, as shown in this experiment, spin up is this dense region. Spin down is this white region. So
literally spin up and down?
Spin, yes. They align alternatively. So this is antiferromagnetic order.
Oh, I see. Thank you.
Okay. And we use quantum master equation to describe inelastic collisions. Here, the jump operator describes, again, two-body loss arising from on-site inelastic collisions. Then the non-hermitian Hamiltonian reduces to the Fermi-Hubbard model with a complex interaction strength like this. So U minus I gamma. So quantum magnetism arises from spin exchange interaction. Suppose that on-site interaction U is much larger than the hopping amplitude T. For anti-parallel spin configuration, the system can lower energy via virtual hopping to the neighboring site, so like this. For parallel spin configuration, the system cannot lower its energy because hopping to the neighboring site is prohibited by Pauli exclusion principle. So we thus obtain an effective antiferromagnetic Heisenberg Hamiltonian from the Hubbard model. Good. However, the situation dramatically changes in the presence of inelastic collisions. For anti-parallel spin configuration, the spin can lower energy by virtual hopping to the neighboring site. So as I discussed in the previous slide. However, once this occurs, then those pairs will be dissipated due to the inelastic loss. So antiferromagnetic interaction is thus suppressed by inelastic collisions. On the other hand, for parallel spin configuration, the system is free from loss and stable. Thus, high energy ferromagnetic states are stabilized by dissipation. So this panel shows the dynamics of spin correlation of non-hermitian Hubbard model with 8 particles. The initial state is an antiferromagnetic nail order, up, down, up, down, up, down. So this panel shows the result of numerical simulation. So what we calculate is this correlation, C, and if this number is 1/4, this means that two spins are parallel. If this correlation is -1/4, this means up and down are anti-parallel to each other. So as time goes on, then all curves converge to a single point. This means the perfect ferromagnetic order which is the highest energy state of the antiferromagnetic Heisenberg model. Therefore, the initial state is antiferromagnetism, but due to dissipation, magnetism is completely inverted by dissipation. So finally, let me discuss topology, symmetry classification, symmetry unification.
Can I ask just one more question?
Yes, please.
In your previous slide,
Yes.
it's probably wild speculation, but what you're describing here, so somehow you converted the system from ground state to the excited state, and
Yes.
excited state is stable under continuous measurement.
Yes.
Seem to remind me of rocket state. Is there any connection between two?
So in what sense do you think this system is similar to Floquet?
So Floquet is basically you do periodic perturbations, and the periodic perturbation here you means continuous measurement. I don't know whether you have a periodic, but in any case you will have a periodicity in that continuous measurement, and that is basically essence of the Floquet physics. And the Floquet physics, we know that excited state become in a say ground state under periodic perturbation. So I just wonder whether any connection between this Floquet physics and the physics you describe here.
Okay, thank you very much. Honestly, I haven't considered this possibility, but let me think. So in the case of Floquet, we perturb the system periodically in time.
Yeah.
Therefore, the spectrum becomes periodically in energy spectrum, energy space.
Yes.
So different energies become equivalent. And this allows the system to be in excited state. Okay.
Yeah.
Okay, so this is the physics of flow. Okay. In our case, there are two situations, being anti-parallel and parallel. And anti-parallel is a higher energy state.
Yeah.
And this is stabilized because, first of all, this state is protected by Pauli exclusion principle. And the lower option, anti-parallel state, is eliminated due to the loss. So
you mean the decoherence, you mean?
Yeah, well, atomic loss. So they just collide and go out of
okay. I see.
So in this
sense,
I see.
Then that's different, right? I see. Okay.
Yeah. I think in this case it's different. Yeah.
Right. Okay. Thank you.
Thank you very much. So now the question is this. So how many topologically different states are available once we go beyond Hermitian is a question I would like to address in this last part, because different topological phases defines how many different possibilities we would have. So
Professor Ueda, before going further, so I wanted to just clarify. So when you define the ground state of the non-Hermitian system, so I think there will be generally complex energy of the many-body system, right? So do you just ignore the imaginary part? Is it criteria, or you just consider real energy? Or
okay, no, we don't ignore, and there is an imaginary part. Therefore, all observation we have here is within finite time.
I see.
So if we wait for a longer time, all atoms are gone. Yes. So, but for our models, as far as the models we investigated, the ground state energy has the smallest imaginary part. Therefore, the longest lifetime.
Is there a reason why, or why it should be, or?
I have no clear reason why it should be.
Okay.
However, for those models we examined, we only numerically checked that
I see.
ground state energy has the smallest imaginary part.
Okay, I see.
Yeah, but this is an interesting question, because if excited states happen to have the smallest imaginary part, then excited states should become the ground state.
Right, right.
Yeah, because it's stable. Yeah. So interesting. Thank you. Yes? Alexei?
Yeah, sorry. Yeah, thanks. It's basically a continuation of the question by Munjib, but did you try to look at, say, a random non-hermitian matrices just to check whether they're lowest in real part of the eigenenergy, the states with the lowest real part, whether they also have the smallest imaginary part? Because the random matrix would be, in a sense, an approximation. I mean, if you confirm it with random matrices, then perhaps that would be a good claim that ground state automatically selects or imposes a small imaginary part.
Very good idea, I think. Yeah. And for chaotic random matrices, I think you can test this even analytically. And yeah.
I think this is probably even known for something like Ginibre matrices.
Ginibre.
Yeah, because that's that's just an ensemble of complex matrices without any specific symmetries.
Yeah, but in this case, is it known that ground state has the smallest imaginary part?
I don't know. I'm just saying that this ensemble was studied, so for sure, people. I mean, there might be results already. I'm just saying that when I proposed random non-hermitian Hamiltonians, one idea was the Ginibre ensemble.
Ginibre ensemble is one class, but also there are other classes as well.
Yes. I just named the one that came to my mind first.
So Ginibre is widely found classes, and yeah, but still, I think it is interesting to check this observation. Yeah, yeah, it might be the case that actually what I have studied is a physical model. Okay, and this Hamiltonian is a physical model because it is known to be stable. Okay, and even in the presence of loss. Yeah. So in this sense, I don't know whether this rule generally holds, but still, yeah. If someone is interested in, I encourage them to test this for analytically calculable model. Okay. So thanks for this stimulating question. So now let me finally discuss how many different topological classes are there once we go beyond Hermitian. So there are three fundamental symmetries in Hermitian systems, that is time reversal, particle Hall, and the chiral symmetries. For each symmetry ramifies into two distinct symmetries once Hermitian constraint is lifted, because original symmetry and its Hermitian conjugate should be different, should in general be different. Furthermore, as I will show later, the time reversal symmetry and Hermitian conjugate of particle Hall symmetries are actually unified into a single symmetry class. So let me discuss how removal of Hermitian constraint ramifies symmetries. Time reversal symmetry is defined by this relation. Here T is a time unitary operator and star denotes complex conjugation. For the Hermitian case, complex conjugation can be replaced by transposition However, they become non-equivalent for non-Hermitian Hamiltonians. Thus, time reversal symmetry ramifies into two distinct classes once Hermitian constraint is removed. A physically complex conjugation implies time reversal, and the transposition actually implies non-reciprocity. Time reversal and non-reciprocity are usually regarded as the same, but this is actually because they are considering Hermitian framework. So they lead to the same physics for Hamiltonians, but could predict different physics for non-Hermitian Hamiltonians. And examples include symmetry-protected topological lasers that support lasing helical edge states, and dissipative topological superconductors that support non-orthogonal Majorana edge states. So I don't elaborate on this, and if you are interested in, then please look at this reference. So let us next discuss chiral symmetry, which is defined by this equation. Since the Hamiltonian conjugate of Hamiltonian coincides with the original one, chiral symmetry can be described by this lower equation as well for within Hermitian framework. However, for non-Hermitian Hamiltonians, they are not equivalent, and we have two distinct symmetry classes. That is sublattice symmetry for the upper one, and the chiral symmetry for the lower one. Because of non-equivalence between complex conjugation and the transposition, the time reversal particle Hall and the chiral symmetries ramify into two distinct symmetries in non-Hermitian physics. So furthermore, non-hermiticity unifies time reversal symmetry and the Hermitian conjugate of particle Hall symmetry. So let us next discuss this non-Hermitian topological symmetry unification. The time reversal symmetry and the Hermitian conjugate of particle Hall symmetry, they are defined by G's conditions. Both of these conditions involve complex conjugation, and hence they are anti-unitary symmetries. The G's symmetry classes become equivalent to each other once the Hermitian constraint is removed. In fact, suppose that a non-Hermitian Hamiltonian H respects time reversal symmetry, then another non-Hermitian Hamiltonian I times H respects the other anti-unitary symmetry with a minus sign here. Hence, multiplication of I, pure imaginary, leads to a 1-to-1 mapping and does not change eigenstates. So we incidentally note that multiplication of I is not allowed under Hermitian constraint, but is allowed within non-Hermitian framework. Thus, the anti-unitary symmetry that are distinct under Hermitian constraint can thus be unified in non-Hermitian symmetric systems. So in Hermitian systems, the celebrated tenfold Alternative-Bauer symmetry class constitutes the fundamental symmetry classification based on time reversal, particle Hall, and the chiral symmetries. In the non-Hermitian case, we actually have 38 symmetry classes. First, there are 10 non-Hermitian Alternative-Bauer symmetry classes. Second, there are 10 AZ dagger symmetry classes. And third, there are 22 non-Hermitian AZ symmetry classes based on sublattice symmetry, which are not equivalent to chiral symmetry for non-Hermitian Hamiltonians. Here, we overcounted 4 symmetry classes due to symmetry unification and non-Hermitian systems. Thus, in total, we have 38 symmetry classes. And this 38-fold symmetry classification is a non-hermitian generalization of alternative symmetry classes. So we now have 38, which is extended from 10. So to summarize, so I have attempted to present an overview of emerging beyond-hermitian quantum physics by focusing on open quantum aspects of physics. So fundamental constraint of Hermitian physics can be lifted in non-Hermitian physics, thereby leading to a number of new possibilities. For example, a time reversal, a time evolution becomes non-unitary, which leads to unique transport and quantum criticality. Eigenstate becomes complex, which leads to magnetic reversal. And eigenstates become non-orthogonal, which allows topological phase transitions without gap closing. Furthermore, the transposition of a matrix is not equal to its complex conjugation, which leads to topological unification and ramification unseen in Hermitian physics. These new phenomena exemplify only a tip of the iceberg of very rich beyond Hermitian physics. So thank you very much for the kind attention.
Thanks, Professor Ueda, for very inspiring talk. So we may have accept some questions from the audiences. So if you have question, you may unmute yourself or raise your hand. We have a question from the Vladimir Villegas. Yeah.
Yeah. Good morning.
Good morning.
Professor, may we go to slide number 62?
62.
62. Yes. 62.
Yes.
Yes, this one. For this one, my question is why is it that we always use the half filling condition for our systems?
Oh, this is by experimental preparation.
Okay. So yeah, so that means that by the preparation or by the mode of the preparation is that you're going to immediately it follows that the chemical potential is, regardless of the temperature. Am I right?
Yes. More specifically, what they do is this. So they can tune interparticular interaction, strongly repulsive. Then the prepared state is a multi-insulating state.
Okay.
So they can just easily prepare a unit filling multi-insulating state. And this is their initial state.
Okay. Another question on slide number 64.
Yes.
This master equation is a Markovian master equation, am I right?
Yes.
I see. Now, suppose that, for example, we use the Feynman path integral, we should recover like the same results as this master equation. Am I right?
Under the assumption of Markov. Yes.
I see. Yes. And then last question on slide number 68.
60.
68.
68.
Yes.
Yes.
Yeah. You said here that, well, for the anti-parallel spin configuration, it lowers the energy. Does this mean that the on-site interaction U is negative?
On-site interaction is positive.
Positive. Okay. Thank you.
Then via this second order perturbation, the energy is lowered. Yes.
Okay. Thank you, Professor.
Welcome.
Okay, we also have a question from Hyokjun Yang.
Oh yes, thank you for very nice talk. And I have a question. I have a trivial question. In your examples of Luttinger liquid and Fermi Hubbard model, it seems that the effect of measurement is to collect some interaction coefficients to be complex rather than real without introducing new terms, then it is possible to introduce new terms which breaks the symmetry of the original Hamiltonian. For example, if the interaction between the system and the best breaks the symmetry of the original Hamiltonian.
I think it should be possible because originally prepared system and the type of loss should be different. So there is always, for example, this type of two-body loss. But if you prepare a system which has a different symmetry from this one, then two-body loss should introduce a symmetry breaking perturbation, non-hermitian perturbation. So although in our case symmetry is the same because we wish to discuss quantum criticality and the effects of loss, but yeah, in general it is possible.
Oh yes, thank you for your answer.
We also have question from Kisop.
Yeah. Maybe not much well defined. So in your last part of talk, so 38 classification scheme. So compared to the tenfold way classification in if I consider some in the perspective of some topological term, some so 38 seems to be quite many. So if I consider some effective field theory perspective, so then we have several, not many, some zeta, Zimmerwitten, and some G2, and several only topological terms. Usually I expect depending on some symmetry. So suppose I'm trying to have some starting from one of, and I'm trying to have some anomaly calculation, fermion, and then I obtain some. Then what I'm expecting. So my question is, 38 is, I will not have 38 kinds of topological terms in my opinion. If I have, so even if I have this symmetry classification, 38 symmetry distinguished classes. So can you, sorry, not well-defined questions, but yeah.
Yeah, I think, okay. Yeah, for example, the question may be rephrased as follows. So can we construct a Chern-Simon effective field theory for non-Hermitian classes?
Yeah.
And if so, then how many different types of Chern-Simon classes can we construct? Well,
thank you.
And then if the number is smaller than 38, then there must be additional constraint due to in creating effective field theory. So can you consider such additional constraint imposed on the Lagrangian? So this is, I think, is a question. And if there are no additional constraint, then I think essentially the same number of Chern-Simon series we can devise.
I see. Yeah, I got the statement itself. Yeah, I see. Yeah, but yeah, let me consider more on this point. Thank you.
Yeah, I think this is creating an effective theory for non-Hermitian is definitely interesting, and I think this is a very interesting question. Thank you very much.
Is there any other questions? Then I have a question. So about this 38 classification. So I think many people, including me, are already used to this tenfold classification. So we have this some physical insight. For instance, if we see some superconductor, it belongs to some class or something like that. So, but in the case of 38 classification, I think it's quite mathematical. So if we somehow see some kind of measurement protocol or something like that, then is there like a insight that we can, oh, this system must belong to some class or something like that?
Yeah, I think tenfold classification is okay with the Hermitian case. So it's very well understood. So I think the key insight in non-Hermitian case is a distinction between sublattice and chiral. So they are usually the same in Hermitian framework. But once you introduce non-Hermitian part, dissipative or open quantum systems, then sublattice symmetry and the chiral symmetry must be distinguished. So this is one important case. Yes, yeah, and maybe concrete example is we can, and also another one is time reversal and reciprocity.
I see.
They are again the same, equivalent within Hermitian, but they must be distinguished. Then what new effect can we expect? These are two examples: symmetry protected topological lasers and dissipative topological lasers, topological Majoran edge states, because those phenomena are generated via the transposition symmetry. Yes. So, and more examples are discussed in this paper.
I see. Okay.
So reciprocity, sublat symmetry, and their distinction from time reversal and the chiral is a key,
okay,
to discover new findings.
Okay, I see. Thanks. We have also another question from Parul Jain.
Sir, I wanted to know the impact of this of breaking the Hermitian physics on the quantum information aspects. Like, can we see something new for people who are working on quantum information from the when you break the all these the various like all these symmetries? How will it how will it impact the quantum information quantities that we're calculating, or if you can say something about that?
Well, okay. I think this is quite an interesting question, and maybe the hint could be summarized in this one. So, for example, usually quantum information is frameworked within Hermitian constraint.
Yes.
But maybe you can relax those conditions. For example, spectrum can become complex. States, eigenstates can become non-orthogonal. Transposition may not be necessarily be equal to its complex conjugation. So if you remove those constraints, then what new possibilities will open in quantum information processing is a question. So my suggestion is that you may look at many theories in quantum information and individually check whether they survive or should be modified in the presence of those relaxing of constraint. Yeah.
Okay, thank you.
But this is not well explored yet.
So is it so are there some people working on the theory and the experimental verification of the impact of the breaking of the symmetries on the quantum information theoretic quantities? Is it possible to go ahead and have a framework for that? And Like, it's just a curiosity because I generally don't get to hear from the non-hermitian perspective.
I haven't heard much, but I feel there is a great potential in this direction. So I'm also curious.
I see. Okay. Thank you. Thank you, sir.
Thank you.
And we have a question from Professor Min-Chul Lee.
Yes, thank you. I'm Min-Chul Lee from Gyeonggi University.
Yes.
And my question is about, actually my question is not discussed in this talk, but it's related to topological nature of a non-Hermitian system. Actually, it's about the bulk boundary correspondence. Does it work for non-Hermitian system still?
Oh, okay. In the non-Hermitian case, bulk boundary correspondence is partially breaks down and should be replaced. I think it is discussed in this review article. And yeah, one notable new effect in non-Hermitian physics is there is an effect called skin effect. Skin effect is an effect in which the density of states is singularly concentrated on the boundary. And this is called skin effect. And the skin effect leads to a partial breakdown of bulk electrical correspondence and also creates a new type of quantum anomaly. Yes. So yeah, modification. So, that is a modification.
Then the boundary state for non-Hermitian system is not well related with its bulk property.
It is related, but because of this skin effect, the certain modifications are required.
I see. Thank you.
Thank you.
Is there any other questions? If not, I think then we had many inspiring discussions. So we thank again for very interesting talk for Professor Ueda. And I think we may end our colloquium session then. Yeah.
Yes.
Thank you very much.
Thank you very much.
Thanks a lot. Okay. So, okay.
Thank you very much, Professor Moonjip.
Oh, thank you. Yeah.
Yeah. Thank you very much. Okay. I'll see you. Bye-bye.